Hello, welcome to the video on Introduction to Functions and Relations. This will be a lesson on this topic, and I got to warn you right now, we're going to be covering a lot of material, so don't feel shy about maybe watching this video 2 times, 3 times, or breaking it up in parts. Okay, that's perfectly fine. But we are going to be covering a lot, so let's get right to it. Our objectives are, we want to go and define what a relation and function are. Okay, and then we're going to determine if a relation is a function. Okay, so already you can tell that relations or functions are connected to one another. And then we're going to look at some vocabulary that has to deal with functions, and specifically it's going to be domain, range, independent, and dependent variables. We're going to tell you what those are, and then we're going to learn how to evaluate functions for a particular value. And of course there'll be some few other things that you're going to want to take notes on. So remember, this is an introductory level video. Okay, it's a lesson, so it's a lot of material, but I'm going to try to keep it at an introduction level. Of course, you want to do the example sets and learn all the other associated topics within this particular chapter. Okay, on functions. All right, so let's get right to it. Functions and relations. So what are they? Okay, what are we even talking about here? Well, functions and relations, okay, are simply a collection of points. That's all they are, okay? So when we define what a relation is, a relation we define as a collection of points. However, a function is a type of relation, so it also is a collection of points. The thing that distinguishes a function from relation is a special type of relation. Okay, now I'm going to tell you what makes functions special from any ordinary relation. Okay, there's some characteristics that make them stand out. And functions in mathematics are extremely important. So once we know that something is a function, then we know a lot about it. Okay, but just to kind of get this lesson going, relations and functions are nothing more than a collection of points. So what do I mean by collection of points? Well, here is various ways you could see a collection of points. Okay, are they not? You could see points maybe on a graph. Okay, an XY graph, you could plot some points and then say, hey, this is my collection of points. Maybe you can even put the coordinates next to your collection. Another way of listing your coordinates without even graphing them, just saying, hey, here's my collection of points. Okay, 1, 3, 3, 7, 6, 13, and then we have these brackets right here. In mathematics, those brackets indicate a set. Okay, that's a fancy math term that means a collection. Okay, so this is a collection of points. Right, so these are all various ways we can describe it. Here we have a table, an XY table of values. Okay, here you can see if I plugged in 1, for example, into this equation of a line, I would get 3. Okay, if I plugged in 3, I would get 7. I plugged in 6, I would get 13, and so forth. Now, some of you might have already picked up that all these particular relations are equal. Okay, we're talking about the same points, and this particular equation here has these points on it. Okay, this line, okay, falls through these points. So, ways that we can identify a relation and a function are by a collection of ordered pairs, a graph, an equation, and by a table of values. But there's another way that you can take a look at a relation. It's called a mapping diagram. Now, most of you, this is probably going to be pretty new. You may not be familiar with this, so you want to pay attention. Okay. So a mapping diagram is the following. What it is, it has an oval, okay, where you're going to put all your x values for your coordinates of your collection of points. You're going to put the x coordinates in this oval, and then you're going to draw a line to the corresponding y coordinate for that particular point. So let's show you what I mean here. So 1, 3 is part of our collection. Now, with the mapping diagram, to represent the point 1, 3, I'd put the 1 here, okay, in my oval, and I would draw an arrow from left to right, very specifically from the x to the y, 3. So 1 has a relationship with 3, okay, that's a relation. So that is equivalent to the point 1, 3, okay. And you can see here 3 is pointing to the 7. Okay, that's the y value of this particular point, so that's the point 3, 7. And then 6 points to 13, representing this point. So this right here is an illustration of a mapping diagram. This is a mapping diagram. Now, why do we like to represent relations in a mapping diagram? Well, I think one of the reasons, there's several, but the main one, and I'm going to choose what I'm going to feel is the main reason, is because it's easy to describe or define what a function is. Okay, so far we've been talking about relations, and we know that functions are some sort of special type of relation. Now I'm going to use a mapping diagram to define a function. Okay, why is a function stand out than just a normal run-of-the-mill relation? Now here's what makes a function special. Functions, okay, their x values, only point to one y value. I'm going to say this a few times. Okay, when you have a function, the x coordinates, the x values will only point to one and only one y value. All right. Let's start taking a look at some examples of things that are not functions. All right. What about this? Okay. So if I had a mapping diagram, and this is my mapping diagram, what would be the points in my collection? Well, I would have the point 1, 3, okay, because 1 points to 3, and I would also have the point 1, 7, because 1 is also pointing to 7. So you kind of think of it this way. You have, well, I'll use the term of a boyfriend or girlfriend, if you will. Let's say you have the same person, the same boyfriend, maybe trying to date or go out with two different people. That's a problem, okay? You see here, this one is trying to go with the 3 and with the 7 at the same time, okay? That is not a function. All right, so if you had a collection of points, let's go ahead and just write them up here. If I said, okay, here's my collection of points, 1, 3, 1, 7, 3, 7, 6, 13, and I ask you if that collection of points, this relation, by definition, is a function, well, one of the ways you can determine that is by drawing a mapping diagram and then determining what you have. Okay? So this is what this is why we like these mapping diagrams. So now I'm going to give you another situation, and I'm going to ask you whether this is a function. Okay? So what do you think? Is this a function? Does this mapping, okay, it's a mapping of a relation, does it represent a function? So remember, the definition of a function, you want to write this down, is where one x, okay, points to one and only one y, or one x corresponds to one and one, or an x value is associated with one and only one y value. There's a number of different ways you're going to see functions defined, but here, based upon what I told you, is this a function? It is, okay, because every x is pointing to one y. Okay, 3 is pointing to 3. It's not pointing to two different y's, and 6 is pointing to 3 also. So yes, this is a function. All right, it's okay that the x values point to the same y value. Okay, they just can't be branching off this way. All right. Another way to determine whether a relation is a function is something called the vertical line test. So you definitely want to know what this is. Okay. Remember, we said that one of the ways we could see a collection of points is by a graph. Okay. So like here, for example, I have a graph, and on this graph, there's all these points. Okay. Now this is quite a collection of infinite points. Okay. So if I had to make a bracket and give you all the points on this that would represent this particular relation, it would be infinite, right? So if we don't want to do that, I'll just give you the graph. Okay. So now that I have a graph, I can use something called the vertical line test, and this is very easy, very, very easy. Okay, and here's how it works. If I can draw a vertical line through the graph, okay, anywhere through the graph. If I move a vertical line and I draw it anywhere through that graph, okay, and it crosses the graph, the function's graph, only once, only one time, it is a function. The graph is a function, okay? So let me say that again. If you could draw a vertical line anywhere through, at any portion, and you could try to break it, you could try to fail it, but no matter what you do, if you draw a vertical line through that graph and only cross it through once, you have yourself a function. Really easy way. So let's take a look at an example. I'll erase this here for a second. Let's take a look at an example. Maybe you want to come up with an example of what fails the vertical line test. Let's give you a quick example. X, Y. So what if you have this? Okay. So here's my relation. You can see this would fail the vertical line test. Now that you know about mapping, I want you to think about it. Let's suppose this is 2, okay? 1, 2. And let's say this is the point 2, 8, okay? I hope you folks are with me. This is 1 and this is 2. So this is the point 2, 8, and this would be the point maybe 2, negative 3, okay? Let's think about what that would look like in the mapping diagram. X and Y. I would have 2 pointing to 8 and pointing to negative 3. Okay? So you can see that this fails. So you could make a mapping diagram, but the mapping diagram, graphically, the way you would see it, how it would fail, is that when you drew a vertical line through the graph, it passes through twice. Okay? So this fails the vertical line test. So this graph does not represent a function. It's simply a relation. Alright, moving on. So if you understand everything so far, you're doing fantastic. Okay, so I'm throwing a lot at you, and if you need to take a break, definitely do so. Alright, so let's talk about more things about functions here. And some of the terminology we were talking about, we want to define, was dependent and independent variables. Okay, basically what you need to know is that the x variable is the independent variable and the y variable is the dependent variable. And let me just kind of remind you here, if you had a graph of a line, y equals 2x plus 1, if you remember, we could graph lines, the equations of a line, by using the table of values, remember? So if I plugged in 1 here for x, that would be my input, okay? I would plug in 1, and I would get 2 times 1 plus 1, so that would be 3. So my y value here, my y value 3 is dependent. It's dependent upon this x value. Okay, it's dependent upon what I plug in for x. And this is kind of like how you want to think of it. Alright, so whatever you plug in for your x values, your y values are going to be dependent upon what you decide to plug in here. Okay? So the x variable we call the independent variable, and the y variable we call the dependent variable. You'll learn a lot more about this later, and functions are going to be with you for a long time in your course of studying mathematics, whether it's Algebra 1, Algebra 2, pre-calculus, so forth. So these terms will keep arriving over and over. Let's move on now to function notation. Okay? So here I said that y equals f of x. Alright, so this mysterious notation here, if this has been intimidating for you, you should just relax and say, hey, this is very easy. This little symbol here means f of x. That's how we pronounce that, f of x. Okay, so f of x equals, this is right here, we would pronounce this g of t. Okay, how about this one? What do you think, how would we pronounce that one? H of y. Okay, so very simple. And all this f of x is, or g of t, it's basically, in its simplest term, we'll use this y example, y and f of x. Y, the variable y, just as I had this equation here, y equals 2x plus 1, is equal to this f of x notation. So f of x, instead of this y here, I'm going to write f of x equals 2x plus 1. Now the reason why we like to write functions in this way is because we have our independent variable, okay, and remember those are our input values. Those are our input values here. So we're going to plug in values, that's our independent value, and then what we get out, the result, is going to be dependent upon what we decide to put in. So here, when I have this symbol right here, it says f and then parentheses 2, this means f of 2. It simply means evaluate the equation and let x equal to 2. Let your independent variable be equal to 2. So what do you think f of 2 is going to be for this particular function? Alright, so x is going to be equal to 2. That's why there's no longer an x in here. We have a 2. So it's going to be 2 times 2 plus 1. Okay, so 2 times 2 plus 1 is 4 plus 1, 5. Okay, so remember up here when we're working with the table of values, we're doing the exact same thing. Okay, let's go ahead and just do one more here with this example. Why don't you tell me what f of 4 is? F of 4. Okay, so you're going to replace the x with 4, so that's going to be 2 times 4 plus 1, so this is 8 plus 1 or 9. Okay, so the value f of 4 is equal to 9. Alright, now we don't have to always have f of x. Okay, you may have what I have over here, g of t, but it works the same way. Okay, look here, t is your independent variable. Okay, it's in the equation. Alright, so g of t equals, and so this is g. Okay, more often than not, if the variable is g, and this here, the independent variable is t, you have the dependent variable, g, and you have the independent variable inside of it, t. Okay, the only exception here is with the f of x. That's kind of a funny exception, but that's just kind of the way it works. So g of t equals 3t squared minus 1. So let's go ahead and find out what g of 1 is. So you're going to replace the t with 1. It's going to be 3 times 1 squared minus 1. So this would be 3 minus 1 or 2. So g of 1 is 2. Alright, of course we're going to do tons of practice and example sets, but that's evaluating functions and function notation. Let's take a look at these concepts here, domain and range. Very important when we talk about functions. The domain is everything you're allowed to put in. So all your input numbers, input values, let's say it that way. Okay, everything that you can plug into the function without the function blowing up. Now what do I mean by that? Alright, I want to tell you what I mean by that, but before I do that, I'm going to tell you what the range is. The range is your output values. This is very similar to your independent variable, independent, and your dependent. Okay? Your range is dependent upon your domain. Okay, the values you plug into it. Okay? So here, when we're talking domain and range, we're almost always talking, by the way, in the real number system. In other words, think of the real number line. We have 0, and you have all the integers, 1, negative 1, 2, maybe negative, square root of 9. Okay, you have the entire real number line. Okay, we're not dealing with complex numbers, nothing like that. Dealing with fractions, decimals, integers, so forth. All right, so let me ask you this: is there any value that you cannot plug in here to x, mathematically speaking? I'm going to tell you right now, no. You can plug in any integer you like. Plug in f of negative 17.2, and you would still be able to get an output value. Okay, negative 17.2 plus 1. You'd use your calculator to figure it out. But basically here, the domain, you could plug in any real number. So the domain is the entire real number set. So you just have your whole choice of any numbers that you want to pick in a real number line to plug into this particular function. And every time you pick any number, you're guaranteed to get, let's see the different color here, you're guaranteed to get some sort of output values. Right? That's not the case with all functions, though. That's not the case with all functions. So before I move on, the domain here was all real numbers, and the range is all real numbers also. Okay? Now, let's take a look at this situation. This is where we start having some interesting examples of domain and range. Okay, so why don't you take a look at this function, f of x equals 9 plus x over x. Okay? What is the one number that will cause you problems here? Okay, it's f of 0. Okay, we cannot have x equal to 0, because if we did, we would have the function f of 0, 9 plus 0. That's okay, but we can never have 0 in the denominator. Okay, this is not allowed. Okay, so anytime we have a function where we plug in a number that creates a 0 in the denominator, or we have a 0 in the denominator, the number that either creates a 0 condition in the denominator, or in fact is 0 in the denominator like we have here, cannot be part of the domain. So the domain here are all real numbers except x cannot be equal to 0. Alright? Now the range would be all the output values you would get excluding x does not equal to 0. And we'll talk more about that. The range is actually a little bit more difficult to find. We actually like to graph these particular functions to determine the range. But that's, I just wanted to get you a general feel of what the domain or range is. This is an introduction now. Okay? Alright, once again we're talking about real numbers. So we have f of x equals the square root of x. Okay, if I had f of 16, no problem. I could take the square root of 16, positive 16, I get plus or minus 4. Alright, so is there any real number that would cause you a problem? You know, f of 0 is okay. The square root of 0 is 0. Well, f of negative 4, or any negative number, will cause you a problem. I challenge you to go to get your calculator and try to take the square root of a negative number. You're going to get an error in your calculator. Okay? In the real number system, okay, there is no such thing. It's undefined to take the square root of a negative number. Okay, this is not allowed. So the domain for this particular function would be what? You can have any real number you like, but it's got to be greater than or equal to 0. Okay? So that's how we would define the domain. So the domain and range, as you become more skilled in mathematics, you take more advanced mathematics, or you study functions, you know, maybe at the Algebra 2 plus level, you really get into, you know, really how to find the domain and range. We're actually going to do some example sets in this series, but if you don't quite understand them, you know, I would certainly try to understand, but you're going to see it over and over again. Yeah, like I said, I'm throwing a lot at you in this particular lesson, so go back, you know, break it up and maybe watch it again. Alright, so let's go ahead and wrap it up. So in review, relations are a collection of ordered pairs, okay? They're just simply a collection of points. Okay, functions are a special type of relation. Alright? And what makes a function special is that each input value, those are the x values that we talked about, correspond or point to only one output value. Those are the y's. Okay, so each x points to only one y, or corresponds to only one y. Okay, we also talked about how we can use f of x as our function notation. We showed you how that works. Okay, domain. Remember, that's all the allowable input values. Okay, you can have anything in the domain as long as you don't get a 0 in the denominator. You can have any number as part of the domain as long as you don't get a 0 in the denominator or a negative inside of a radical square root. Okay, and then a range is all the output values based upon whatever your domain is. We also talked about that we can use this vertical line test to determine if a relation is a function. That's a great tool to know. And then we talked about evaluating a function means to substitute a value for a variable and simplify, like f of 2, okay, is evaluating a function for 2. Okay. A lot of material thrown at you. Okay, I'll say it one more time. If you were able to watch this video and you feel like you got it, that's great. You need to go practice an example set and then come back to the lesson one more time. It's a lot of material just to capture it once, but I felt obligated to give it to you at an introduction level because it all it all ties in. It's closely related, and I thought it'd be best served in one video. Okay, definitely to see over the example sets. Good luck.